This week, our show highlights alternate sources of energy, natural gas, tidal energy, and green fuel. Our civilization might well be called the oil age. Unfortunately, petroleum is far from perfect. Acid rain, global warming, and urban smog all result from its use. However, a well-known relative of oil, natural gas, is a very attractive alternate source of energy. Natural gas occurred millions of years ago in shallow seabeds. It is believed that over the centuries, plant and animal microorganisms accumulated on the ocean floors. Particles of rock gradually covered them, forming a solid called parent rock. Within the parent rock, a slow process of decomposition transformed the organic debris into hydrocarbons. Hydrocarbons are compounds made up solely of carbon and hydrogen atoms. Some of the molecules have less than 4 carbon atoms. Such hydrocarbons, said to be light, are the main constituents of natural gas. The chief one is methane, a molecule that has 1 atom of carbon for every 4 hydrogen atoms. Once extracted from the deposits and rid of its impurities, natural gas is transported to distribution areas. For long distances, it is transported in liquid form by methane gas tankers. Once unloaded, and before being distributed to users, it undergoes various treatments. For safety reasons, a small amount of a chemical substance containing sulfur is pumped into the gas. This laboratory-controlled addition makes the gas smell so that any leakage can be detected. Like coal or oil, natural gas is a non-renewable fossil fuel. However, it is a good substitute for petroleum, especially in car engines. Indeed, in many ways, natural gas is less polluting than gasoline. The main product of gasoline combustion is carbon dioxide. While not harmful to health, carbon dioxide traps the sun's infrared rays. It also traps the heat reflected by the Earth's surface at night. Normally, that capacity to retain heat is beneficial. However, since the beginning of the industrial era, the levels of carbon dioxide in the air have been increasing at an alarming rate, largely due to gasoline-powered engines. Scientists fear this will eventually disrupt the Earth's climate. Gasoline has other negative effects on the environment. In an engine, its combustion is never complete. It produces, for instance, dust, unburned hydrocarbons, and such intermediary compounds as carbon monoxide and nitrous oxide. While they sometimes have short lifespans, these substances are very often toxic. In addition, they degrade under the influence of solar rays. In some major centers, this will produce what is known as smog, a combination of smoke and fog which promotes respiratory diseases and cancer. Gasoline also contains sulfur, combined with atoms of oxygen and hydrogen. Sulfur atoms produce sulfur dioxide, a toxic gas which also forms acids. These air pollutants are the principal cause of acid rain, which affects ecosystems in many parts of the world. Compared to gasoline, natural gas has many environmental advantages. Its combustion is more complete than gasoline's and produces no dust. Moreover, it generates few intermediary compounds, such as unburned hydrocarbons, nitrous oxides, and carbon monoxide. Natural gas, therefore, contributes very little to urban smog. Unlike gasoline, natural gas, once rid of its impurities, no longer contains sulfur. So its combustion does not produce sulfur dioxide, which is so harmful to health and the environment. Conversely, natural gas promotes the greenhouse effect, the absorption of heat by atmospheric gases. While its combustion releases 1/4 less carbon dioxide than gasoline, its unburned methane emissions have a greater capacity to absorb the sun's infrared rays. Only a small portion of methane emissions, however, comes from using natural gas. Methane emissions come mainly from the decomposition of organic matter in dumps and to agricultural activities, especially the manure from ruminant animals. No effective means has yet been found to reduce methane emissions. Still, scientists agree it contributes less to the greenhouse effect than carbon dioxide does, since there is 6 times less methane released into the atmosphere annually. To use natural gas as engine fuel, all that's needed is to fit an engine with an intake system and a special fuel tank. Gas refueling systems for vehicles already exist in several parts of the world. The natural gas is compressed and stored in tanks. A flexible pipe is used to fuel the vehicle, the same as in any conventional gas station. An engine that has been adapted for natural gas has about 10% less power than the conventional engine. However, vehicles powered by natural gas enjoy almost as much freedom of travel as gasoline-powered ones and have greater operational flexibility. Natural gas may not be the panacea for all our energy and environmental problems, but of all the fossil fuels, it is the least polluting and could therefore gradually replace petroleum products.
Fossil fuels such as coal, natural gas, and petroleum are extracted from the subsoil. The ocean also holds a wealth of energy. The tides, for instance, are capable of producing huge amounts of electricity.
Nowadays, energy production and environment protection go hand in hand. Thanks to tidal power, large quantities of electrical power can be produced without harming the environment. Indeed, tide mills have access to a free, environment-friendly, and boundless source of energy. Tides are due mainly to the attraction the moon exerts on the Earth. That gravitational force causes ocean water to be drawn towards the moon. The pull is greater on the side of the Earth that faces the moon, but it also occurs on the other side of the Earth. About midway between these two high tide areas are low tide areas. Because of the Earth's rotation, the level of the sea at any given spot on the planet rises and falls roughly twice a day. With few exceptions, all oceans and seas are subjected to 2 daily tides. Tidal power worldwide is estimated at 3 billion kilowatts. However, this immense potential of energy cannot be completely harnessed. There are, in fact, only about a dozen places in the world that are suitable for the construction of tide mills. An industrial-sized mill requires tides of great magnitude. The difference between high and low tide levels has to be at least 10 meters. In addition, the mill has to have access to an immense water reservoir, as big as possible. It must therefore be built in a bay or an estuary, the mouth of a river. A barrier or barrage in which an electric power station has been installed separates the bay or estuary from the sea, creating a reservoir. All that has to be done to produce energy is to vary the water level between the sea and the reservoir. The first step consists of filling the reservoir. The incoming tide is allowed to flood the reservoir. Sluice gates are closed at high tide when the levels of the sea and the reservoir are the same, and reopened only when the tide flows out. At the turn of the tide, the reservoir is at its highest level. When the difference between the sea and the reservoir levels is sufficient, the outgoing water flow drives the barrage's turbines. Also called bulb generators, the turbines are encased in a metal hull and immersed in a hydraulic conduit. The turbine comprises a 4-blade propeller that harnesses the energy from the outgoing flow. The propeller shaft drives an alternator which produces the electricity. In the final stage, the energy supplied by the bulb generators is relayed to the electricity power supply system. The quantity of energy produced depends on how high the tide is and on the amount of water stored in the estuary. The turbines have the advantage of being able to operate from either direction. Indeed, they can be made to operate when the tide is rising. As it flows into the estuary, the seawater makes the blades turn in reverse direction. Thanks to this two-way operation, energy can be produced nearly 70% of the time. Bulb generators are also used as pumps to artificially raise the level of the estuary to above sea level. Whenever possible, this is done during off-peak periods when energy demand is low, at night for instance. The pumped water is later emptied back into the sea when energy demand is higher. A tidal mill's operation is dependent on the natural intensity and rhythm of the tides. Attempts are being made, however, to allocate production to meet energy demand. To do this, weekly programs are developed. These programs take into account anticipated consumption as well as tidal cycles, which are precisely calculated way in advance. Sluice gate opening and pumping times are therefore programmed in such a way as to ensure the mill maximum productivity. One of the main advantages of a tidal power plant is that it produces vast quantities of energy without polluting the atmosphere. To build the world's first industrial-scale tidal power plant in France, the estuary had to be completely cut off from the sea. This technique may well be abandoned in the future because it initially has a major impact on the region's ecology by interrupting the tides almost completely. During the first few years, only the hardiest species of wildlife survived. However, the scientists observed that after these initial drawbacks, nature gradually reclaimed her own. Today, wildlife in the estuary is richer than before. New species of fish now gorge on abundant food supplies. And numerous birds have come to inhabit its shores. A new ecological balance has been established.
Plants are also high in energy. Heating with wood is an age-old use of the biomass, but it contributes to deforestation. However, researchers have found that numerous other plant species can be converted into renewable, non-polluting energy.
Road transport is one of the main causes of air pollution. Every year, motor vehicles release millions of tons of pollutants into the air, harmful both to health and to the environment. The chief culprit to blame for these polluting emissions is gasoline combustion. However, the world's oil reserves are not inexhaustible. Attention has recently turned to plants as a means of producing clean and renewable energy. Plants have the amazing ability to use light to convert the carbon dioxide in the air into energy-rich substances. Composed essentially of carbon, these substances constitute the biomass. The biomass can be a useful source of liquid fuels called organic or green fuels. Green fuel can be produced from plants containing sugars, beets for instance. The cellulose found in wood and the starch in wheat are also sources of green fuel. Starch, for example, is made up of long chains whose links are glucose molecules. These chains are stored in the grains of the plant. Industry uses starch, for instance, to make bioethanol, an alcohol designed to round out conventional fuels by replacing their lead-based additives. In bioethanol factories, the grains are first cleaned, then lightly ground to remove their hulls. The meal resulting from that first process is then mixed with water. This yields a paste to which enzymes are added. These organic substances act like pincers. They cut the long starch chains into units of glucose. The syrup obtained is then poured into a large vat filled with yeast. This is the fermentation stage. The yeast consumes the glucose present in the syrup and converts it into bioethanol and carbon dioxide. At this stage, the alcohol is still filled with water. It is therefore distilled, then dehydrated by going through a vapor-heated column. Lighter than water, the alcohol migrates to the top of the column, where it is collected in the form of vapor. The residues generated by this process are recoverable. Essentially composed of proteins and fibers, they are clumped together in pellets called brewer's grains. These can be used as cattle feed. Bioethanol can be used in engines as is or mixed with gasoline. It is not, however, adapted to diesel engines. Another biofuel, diester, was developed especially for diesel engines. Made from colza or sunflower seed oils, the characteristics of diester are similar to the gas oil used in diesel engines. Generally speaking, biofuels do not diminish vehicular performance. Moreover, unlike conventional fuels, they have little impact on the environment. Most toxic emissions from vehicles are produced by incomplete combustion of gasoline or gas oil. Biofuels offset some of these drawbacks. Their molecules are high in oxygen, which promotes all-round burn. This reduces unburned hydrocarbon emissions by 30%. Another argument in favor of biofuels is that, unlike fossil fuels, they do not alter the Earth's atmospheric balance. Each year, fossil fuel combustion releases 5 billion tons more carbon dioxide into the air. In the long run, continued increases in carbon dioxide levels could lead to a global warming, the likes of which are hard to imagine. When burned, fuels produced from plants also emit carbon dioxide. They do not, however, increase carbon dioxide levels in the air. This is because burning a biofuel simply recirculates the carbon dioxide already present in the ecosystem in the form of biomass. In this sense, biofuels do not contribute to higher carbon dioxide levels, nor do they emit toxic pollutants such as lead, nitrites, or sulfur. Biofuels do, however, have their faults. In burning, they release aldehydes, compounds derived from ethanol. These compounds are not carcinogenic, and have no negative effect on the environment. But at high levels, they have an unpleasant odor. This is especially true of de-esters derived from plant oils, which let off a smell of cooking fat. For this reason, they are mostly used to fuel tractors rather than city vehicles. Our concern for a clean environment is prompting us to look to alternative and less polluting sources of energy. Fuels in liquid form are easier to store and transport than any other form of energy. This makes green fuel a most promising energy source.
The solution to our energy problems will require that we diversify our sources of supply. Ideally, there should be as many windmills and solar panels as there are gas stations.